Okay, continuing with example 1. I had to plug in my iPad, so we kind of take a little break here, clear the screen, and just kind of give ourselves a little bit more room. I've recopied the equation where we're at right now. Again, we did our substitution. We're trying to separate this thing. To make things a little bit easier, let me distribute this u in so I can keep that function of u together. We have x squared times 1 plus u squared dx plus this is x squared u minus u squared dx equals negative x cubed 1 minus u du. If I look at my left-hand side, I have two terms. They both have an x squared and a dx, so I'm going to factor that out. And I'll just kind of put it here at the back end. When I factor out that x squared dx, we're left with a 1 plus u squared plus u minus u squared equals negative x cubed 1 minus u du. These u squareds cancel, so we're left with 1 plus u times x squared dx is equal to negative x cubed 1 minus u du. And now let's go ahead and let's separate our variables entirely. On this left-hand side, I only want there to be x's, so I want to remove this 1 plus u, which is multiplying. So I'm going to divide both sides by 1 plus u. And then similarly, on the right-hand side, I want there to only be functions of u. So I would prefer to remove this negative x cubed. So I'm also going to divide both sides by negative x cubed. And let's see what that does for us. On the left-hand side, these cancel. X squared divided by negative x cubed will give us a negative 1 over x dx. This is equal to, on the right-hand side, these cancel, and we have 1 minus u over 1 plus u du. And we have indeed ended up with a separable differential equation. To solve for u, we're going to integrate both sides. The antiderivative of negative 1 over x, we know that that's going to be the negative of the ln of the absolute value of x. And I'll put my plus c there. It's equal to, now this is a fun one, something we haven't seen yet in our class. To integrate this rational function, notice that it's not in proper form because the degree of the numerator is at least equal to the degree of the denominator. So you have to do a long division on this, or you could do synthetic division. But I need to actually divide u plus 1 into negative u plus 1. So actually do long division, take the denominator, divide it into the numerator. U plus 1 will go into negative u plus 1 negative 1 time. This will give us negative u minus 1, and then we subtract, oops, come back. So it goes in negative 1 time, we subtract, the subtraction is addition to the opposite, these cancel and we get 2. So the quotient is going to be negative 1 plus 2 divided by 1 plus u, or I can call it u plus 1. So this is the antiderivative of negative 1 plus 2 over u plus 1 du. Now we can go ahead and integrate that. We have the negative of the ln of the absolute value of x plus c is equal to the antiderivative of negative 1 is going to be negative u plus, to do this one, it's a u substitution, but you're going to get 2 times the natural log of the absolute value of u plus 1. And there we have it. So this will give us our function u. Now remember, so at the end of the day, what this kind of gives us, and I guess we could kind of play around with it a little bit. But let's go ahead and wherever we see the u, remember what was u equal to? So u in the beginning, if y equals ux, then u is equal to y divided by x. So we have the negative, the natural log, the absolute value of x plus c is equal to the negative of y over x plus 2 times the natural log of the absolute value of y over x plus 1. We can use properties of logarithms to try to rewrite this thing, so let's kind of go ahead and do so. I'm going to bring all of my logs to one side and all of my non-log terms to the other. So we have c plus y over x equals, bring this log term to the other side, we have 2 times the natural log of the absolute value of y over x plus 1 plus the natural log of the absolute value of x. Power rule says we can bring this on the inside. So we have now c plus y over x is equal to the natural log of the absolute value of y over x plus 1 squared plus the natural log of the absolute value of x. So let's make some more room over here. Let's see how much more we can simplify this thing. So we have c plus y over x equals, again, if you have an, this is the product rule for logarithms. This is going to be the ln of the absolute value, and we can multiply on the inside. This thing here, by the way, let's simplify that. So we have y over x plus 1, which would be y plus x over x if you get a common denominator. So we have the ln of y plus x over x. And don't forget that that part was squared. And now on the inside, we're going to multiply it by x. That's coming from properties of logs. So we're going to get c plus y over x equals the natural log of the absolute value. We can do y plus x squared. Now we would also have an x squared in the denominator times x to the first power. We'll now make that an x to the single power in the denominator. We can now raise both sides to the e power. So we have e to the c plus y over x equals e to the ln of the absolute value. And realistically here, because this top term is squared, you wouldn't need the absolute value over that piece of it squared. You would still need it over the x, which is kind of in there in the denominator. So we get, this cancels. We have e to the c plus y over x equals y plus x squared divided by the absolute value of x. Whoa, come back. That was weird. Let's see. So where were we? I'm not sure what happened. My apologies. That's not distracting at all, right? So we had c plus y over x. And now on this right-hand side, when that thing canceled, we had y plus x squared times the absolute value of x. Let's clear off the fractions by multiplying both sides by the absolute value of x. And we get a pretty nice form of this thing. So we have the absolute value of x, e to the c plus y over x equals, this cancels. We have y plus x squared. We've seen this trick before, but the absolute value of x could be plus or minus x. This thing is e to the c times e to the y over x equals y plus x squared. This is a constant. E to the c is a constant. We can just write that as a constant, and we can also absorb the plus minus sign into that constant. So we'll call this cx e to the y over x equals y plus x squared. And that's our solution. It's a pretty nice form that implicitly defines y as a function of x and would be the solution to our differential equation. One of the things I think that you will notice probably as we kind of near the home stretch of this problem, and maybe it's something you probably have already encountered perhaps in the Calculus 2 or Calculus 3 class, is you very well might have the correct solution, and you might very well have the correct answer. But if it was old school and you were trying to look it up in the back of a book perhaps, or maybe even as you're trying to enter things into WebAssign, it might not fully accept your answer as being correct. Even though it might be correct, it might not necessarily be in either the simplified form, or there might be more that you can kind of do to it. Okay. Again, don't be discouraged by that. Oftentimes, there's more you can do to kind of rewrite these things to simplify it and whatnot. But certainly, it's a good exercise to, if you are convinced and you know you have the right answer, but yet if things aren't matching up, try to analyze your solution. Ask the question, what can I do to simplify this thing? How might I rewrite it perhaps? Could be just an issue of doing something with a constant, or maybe you did something bad with a constant that you weren't able to do. But if you have any questions, please ask me about these ones.